Good evening, student. We will wait for a few minutes, so remaining student can join. Then we will start. Okay, good evening. We should start now. So today we will discuss about the fifth week of analytical chemistry course, and I will discuss about the topics which are covered in week 5, and then we will discuss about the assignment of week 5 of last semester. Okay. So first of all, spectrochemical method of analysis. How we will use spectrochemical method of analysis, what are the importance, what are the type of spectrochemical methods, we will discuss step by step. So first of all, we know that how we can analyze spectrochemical methods are, first of all, just a minute. Yes. So wavelength is very important. Wavelength lambda. Okay. So lambda is very important in point of spectrochemical point of view. Okay. Why lambda is important? Because it is lambda is characteristic for a particular metal or a particular organic compound, and like that. So that's why we generally measure lambda, and we characterize our element or our compound or our molecule, whatever in our we are taking as analyte, as a characteristic wavelength. Okay. So in photometer or spectrometer, absorbance of any sample, suppose you have a sample in this beaker, so absorbance of any sample is directly proportional to concentration. Okay. So this is also called as a Beer's law. Okay, we have already discussed Beer's law. Okay, and A is also proportional to we can say B. Okay, thickness of this vial, suppose this is the thickness, okay, suppose it is few centimeter, okay, x centimeter. So it is also depend upon the thickness of this vial. So we can say A is proportional to C. This is the Beer law and this is the Lambert law, okay, Lambert's law. So finally we can say A is proportional to both concentration and thickness of this sample, okay, concentration of this sample as well as thickness of vial, okay, where you are taking sample. So if we will remove this proportional sign, then A will be equal to epsilon C and B, okay, where epsilon is molar absorptivity, okay. So here C is concentration, okay, so concentration is generally taken in mole, and B is thickness of this vial, so you can take as a centimeter, okay. So by this way you can calculate the unit of molar absorptivity, how it will be A upon CB, okay. So absorption has no unit, okay, so it will be only concentration mole, so mole inverse upon B, so B will be measured in centimeter, so centimeter it is, okay. So like that you can calculate its unit also, okay. Second is absorbance. Absorbance is equal to minus logarithm of T, or you can say A is 1 upon log T, okay. So sorry, okay, from here also you can understand that T for transmittance, okay, T for transmittance and A for absorbance. So H absorbance will be in H transmittance will be increased, okay, absorbance will decrease, okay. So transmittance means what? When your rays are passing from the sample, okay, and if transmittance is high, means your sample can absorb very less amount of energy or less amount of wavelength, okay. So this is A is equal to log T, or you can say minus log P upon PO, or you can say minus log I upon IO, okay. So these are the this is the relationship between absorbance and transmittance, okay. So now we will discuss a general view how spectrometry or how spectrometer work, okay. So I will discuss about okay, how spectrometer work. So first of all there will be a light source, okay, we can say this is the light source, okay. For visible light we generally use tungsten lamp, okay. Why we are using tungsten lamp? We know that because it will emit light of the you can say it will emit wavelength or radiation in the visible range. Second, UV. For UV source we generally use deuterium lamp, which is D2, okay, deuterium lamp. So when light will pass from, okay, so suppose you are using suppose we are using a tungsten lamp, so it will emit all visible rays, okay. Means if it is emitting white rays which contain all means color, vigor, but we need a particular wavelength light. Okay, so here we will use a monochromator, okay, which will screen light. Okay, monochromator, or it is also called as a wavelength selector. Okay, so from monochromator, required electromagnetic rays will pass. Okay, and then it will follow sample. Okay, this is your sample. Okay, so suppose intensity of light is IOA. IO means it is initial, and IF means final. Okay, so the intensity of light will be decreased. Okay, why it will be decreased? Because some absorption will be there in sample. Okay, finally it will be passed. Okay, and it will follow transduction. Okay, so transducer will means read what are the signal are coming from the light transmitting from the sample. Okay, and it will amplify the signal, and this signal will go to detector. Okay, so detector will give you output in the form of chart paper, or it can be on only monitor, okay, of your computer. So this is general, we can say, general outline how spectrometer work. Okay, or in simple words we can say only that light is coming, light is coming and passing from the sample. Okay, and we are measuring what is going on in the this area, means how much light or how much electromagnetic rays are absorbing in this region. Okay, so according to that we will identify which elements are present in your sample. Okay, or we can say which analytes are present in your sample. Okay, according to data output. Okay, so I have already told you that lambda are generally very specific for particular analyte. Okay, and about that we will discuss more. So Beard and Lambert law already we have already discussed. Okay, so now we will discuss about the how your absorption graph will be look like. Okay, okay, so these are the two axes. This is absorption, and this is the wavelength. Okay, and suppose you are getting this type of curve. Okay, so you can say this is the lambda 1. Okay, here you are getting, so it is lambda 1, here it is lambda 2, and here it is lambda 3. Okay, so suppose this value is 280 nanometer. Okay, so this value will be specific for particular analyte. Okay, so you can correlate that if 280 nanometer peak is coming, then it might be this analyte. Okay, particular X analyte suppose. Okay, okay, so just a minute. Okay, similarly other analytes also you can identify, or it can be metal ion, okay, organic compound, whatever. So you can identify their presence in your sample. Okay, so again the lambda, I have already explained that lambda is inversely proportional to its frequency. Okay, or it is inversely proportional to its energy. Okay, so if you are moving from if you are moving in right hand side, okay, so lambda is increasing means energy is decreasing. Okay, so this concept should be clear. Then yes, One more concept discussed in lectures, that suppose we have any analyte which will give many, suppose in vapor phase, okay, in vapor phase it is giving many peaks, okay, like many peaks are there, okay, but in some solvent, non-polar solvent, first it will give only some peaks, but in polar solvent it will give a broad peak like that, okay. So this is in vapor phase, okay, then it is non-polar solvent, and finally it is polar solvent like water. Okay, so why we are getting different peaks, okay, if from vapor to non-polar solvent and non-polar to polar solvent, because here in first when it is vapor phase, okay, so we can interpret with all the energy level, okay, what is the meaning of energy level, okay. So we in last class I discussed that suppose this is your atom, okay, these are the suppose classes, okay, and one electron is here, and when electron get energy and it will jump in higher energy level, okay, it will called as a excited state, okay. So these are the energy state in any atom, suppose, okay, suppose this is the E1 and it is E2, okay, and the electron is jumping from here to here. So it is called electronic state, okay, but it is not like electronic state only, okay, there is some vibrational state and rotational state also, okay. So how it will be look like, so in between there is some rotational state, okay, so we can say R1, R2, okay. So in between rotational state there is some sorry, it is not rotational, vibrational state, okay, just a minute. Because vibrational has higher energy compared to rotational, okay. So here there will be some rotational state also, okay, it will go out as a rotational state, okay. So like that there are different type of energy state, okay. So when electron or we can say it is, okay, when electron will jump from one energy state to another energy state, it will give electronic transition, okay, but when vibrational state will be changed and rotational state will be changed, it will give magnetic peak when it is in vapor phase. But when it is in non-polar solvent, then its vibrational and rotational transition will be disappear, okay, and you will get only electronic state transition, okay. But when it is in polar solvent, okay, so in polar solvent like water, what will happen, intermolecular interaction will be there, okay, and due to intermolecular interaction electron peaks will be merged, okay, and it will give a broad peak like that, okay. So these are the different type of peaks will be available, okay. Absorption spectra also affected by temperature, pH and electrolyte concentration, okay, and sometime it is also affected by interference also, okay, means suppose you are going to analyze particular metal and some other metal is present which is interfere its recognition, then also it will create a problem, okay. So why it is so, suppose you have any suppose you have metal which need to analyze, okay, which is NS plus, okay, when it will react with reagent, it will form MR n minus 1 plus. Okay, why it is? Because it is n plus and you are adding only one reagent, so it will be n minus 1. So when pH will be changed or temperature change, okay, or electrolyte concentration will be changed, it can be dissociate. Okay, it can be dissociate, or it can be make another product. Okay, that's why what will happen, your absorption of the sample will be changed. Okay, and you will get different peak, okay, by changing of temperature, pH and electrolyte concentration. Okay, so these things should be kept in mind. Then one more concept which need to clarify here, that if there is sulfate solution, okay, if sulfate or phosphate is there, okay, in your analyte sulfate and phosphate is already there, so it will create a problem because these are the colorless solution and it will decrease the absorbance of your analyte. So okay, to rectify this error, we use standard addition method. Okay, so what is the standard addition method? So suppose we measure absorbance, and we can say, so this is the concentration. Then we add a minute amount of analyte, okay, non minute amount of analyte, and then we will measure A plus A1, then it will give C plus C1, then again we will add some analyte, then we will measure C plus C2, okay, and like that we will get one relationship, okay, and according to that we can correct, okay, how much absorbance is decreasing due to presence of the sulfate and phosphate ion. Okay, so by this way we can correct our result. So in spectrophotometer, okay, it is not for very high range, high concentration. If your concentration is very high or if your concentration is very low, then it is high probability that your instrument will give wrong result. Okay, some error will be there. So if 90% of transmitters, okay, means what is the meaning of that? That suppose these rays are falling on passing from this sample, okay, here suppose it is 100, so here it is 90, okay, means only 10% is absorbed, so 90% transmitters. Okay, why only 10% is absorbing? What mean to say here is that your sample is very dilute. Okay, so concentration of analyte is very low. Okay, so it might give a wrong result. Similarly, if your transmittance is only 2%, means what? Suppose these are the rays, so means 98% of electromagnetic rays are absorbing in sample. Okay, so only 2% rays are passing. So it is showing that concentration of your analyte is very high. Okay, it is also not good for spectrophotometer and it will give error. It will also give error. Okay, so in both case we will get error. Okay, so if concentration is higher, then we can dilute it. Okay, we have a method which we have already discussed, so we can dilute it. Okay, and after dilution we can get corrected. Okay, then in our UV and UV plus visible. Okay. So UV and visible are very useful electromagnetic rays for analytic chemistry, and it is range between 180 to 780 nanometer. Okay, so this range is very important. Okay, so so how why means which range will be end of visible? This is okay, because UV is means UV has high energy, so lambda will be low, like 180. Okay, so visible range we know that it is around 400 nanometer to 780 or 750. Some books it will mention 750 and some 780 like that, but you need only idea. Okay, so like that, and below that, below this wavelength will be considered as a UV. Okay, UV wavelength. So this is very useful electromagnetic radiation in the form of analytic chemistry. Then we will discuss about the chromatophore. Chromatophore means which will give color. Okay, chromatophore. Sorry. Okay, chromatophore means it will give color. So suppose we have these groups are there, diazo group. Okay. Okay, similarly alkane, alkyne. Okay, so these are the groups which will give which is responsible for color. So we have already discussed that in chromatophore generally two type of transition are very important, which are pi star and pi star. Okay, so this is the forbidden transition. Okay, so its epsilon value will be very low. Okay, but it is symmetrically allowed transition, so its epsilon value will be very high. So this is very, in these two transition also pi star transition is very important. Okay, to identify different element. Okay, so then sometime conjugation is also happen. So what is conjugation? Just a minute, let me explain. What is the conjugation? Okay, so suppose this is the carbon chain. Okay, and suppose there is double bond, like that, alternate double bond is there. Other valency you can satisfy, it is will be CH2, then CH, 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 CH and CH2. Okay. So if I will number this carbon atom, then 1, 2, 3, 4, 5 and 6. Okay. So this is the sigma bond and this is the pi. So pi bond means all this pi bond is made by 2 electrons. Okay, so it will be 2 electrons here. Similarly, these 2 electrons are also there. Similarly, here also. Okay, so what will be happen? It can be like that, CH2. Okay, CH. Then okay, suppose these 2 electrons are shared by this carbon 1 and carbon 2. So carbon 1 is again taking its electron back. Okay, so 1 electron will be there, then it will be CH. Similarly 3 and 4, so 3 again taking its electron, and 1 electron will be like that, then CH, similarly. Okay, so we can say that each carbon atom has 1 electron. Okay, so now carbon 2, which is initially sharing electron with carbon 1, now it can share its electron with carbon 3. Okay, so again it will be make bond like CH2, then CH double bond CH, then CH. Now this electron is sharing with this one. Okay, and finally CH2. Okay, so what is happening? This is a compound is same, but the position of pi electron is changing. Initially it was here, now it is here. Okay, initially it was in between 1 and 2 carbon atom. We are taking only C1 and C2. Okay, but in second case it is in between C2 and C3. Here it is C2 and C3. Okay, so what is happening? Position of double bond is changed. Okay, so overall, to justify this thing, we can say, okay, it can be found in any form, okay, which we discuss here. So finally we can say this type of confusion can be removed if we can say that double bond will be here also. Okay, partially we can say, means we are not sure where is double bond, so it can be with carbon 1 and 2 or 2 and 3. Similarly you can, okay, so overall what we are going to say that there is electron cloud is spreading, okay, in this carbon chain. Okay, so this is called as a conjugation. Similarly in benzene also, okay, this is benzene structure, okay, and similarly you can draw like that also. Okay, so both are same. Okay, only what is happening, only the position of double bond is changing. So overall you can say, if you are drawing the benzene structure, you can say this is the, sorry, it is not outside, it is only inside. Okay, like that. So this is the electron cloud, okay, which is spreading in between all these, among this all carbon atom. Okay, so this is called as a conjugation. This is also called as a resonance structure. Okay, okay, so if conjugation will be increased, uh, then compound need less energy. Less energy means high wavelength. Okay, if conjugation is there, compound need less energy, means high lambda. Okay, because energy is inversely proportional to lambda. Okay, so for to understand this thing, we will discuss some example, like C6 S3CH double bond CH2. Okay, it has only one double bond. Okay, so it will give lambda max at 177. Okay, and epsilon max at 13. Okay, so similarly if you compare this thing with CH2 CH CH where there is double bond. Okay, so this double bond can be conjugate. Okay, how it will be, means I just explained that, means these two electron will be, if this double bond will be break, one electron will be there, one electron will be there. Similarly one electron here, one electron, so it can make also double bond. Okay, so overall electron clouds will be spread over this carbon chain. Okay, so it is conjugation will be there. Okay, so it will absorb at less energy, lambda maximum at 217 only. Okay, lambda is increasing, means energy will be decreased. Okay, and the epsilon will be also increased. Okay, similarly other groups are also there in organic compound, which are very useful to, okay, this functional groups, or you can say this chromato 4, are also very useful to identify compound in analytic chemistry. Okay, so spectrometer is very useful to identify organic compound, biomolecule, drugs molecule, and metal ion also. Okay, then suppose So why it is so? Okay, now we will discuss about metals. Okay, why metals are giving color, different color. Okay, generally transition metal. Okay, generally transition metals are giving very beautiful color, and which can be used to identify them. Okay, so why it is so, and what is meaning of transition metals. Okay, for that we need little knowledge about periodic table. Okay, how our periodic table will be look like. Okay, if you see your periodic table, it will be look like that. Okay, I am only drawing outer, means outer view. It will be like that. Okay, so this is the S block, this is P block, this is the D block. Okay, and here at the end of this periodic table are two lines which is called lanthanoid and actin. Okay, so this is the periodic table. So why we are means why its name like AS, PD. Okay, because electrons are filling in S orbital, P orbital or D orbital. Okay, suppose you are taking iron, so iron will be like here. Okay, so what is the meaning of iron? Okay, it will give you a outer view, means how it is useful in analytic chemistry. So Fe26. Okay, if you write the electronic structure of iron, so it will be 1s2, 2s2, 2p6. Then okay, so first class is filled, second class is filled, then 3s2, 3p6, then 4s2. But third class also has d orbital, so you need to fill d orbital, and d orbital can fill 10 electron. So how much electron we need to fill? So 10, 10 plus 10, 20, and 5 electron will be here. Okay, so in d orbital there will be 5 electron. Okay, so dd transition will be there. How it will be there? When so there are 5 orbitals. Okay, you need to memorize that there are 5 types of sorry, there are 5 d orbitals. Okay, total how many d orbitals? So 5 d orbitals are there, and it is called as a, okay, don't worry about how it will be called. Now this d5. So if I will draw outer line, it will be like that. Okay, for it is very deep concept, but for general to make a general concept in your mind, you just keep in your mind that there is 3 d orbital which has less energy compared to these 2 orbital. Okay, suppose this is first, second, third, and these are the fourth and fifth. So first, second, third has lower energy compared to 4 and 5. Okay, so what will happen? Suppose one electron is there. Okay, so one electron is there. So this electron, when a particular energy radiation will fall on this element, this electron will jump from here to here. Okay, so this is the d orbital, and this is also called d orbital. So the electron transition is being happen in between d to d orbital. Okay, that's why it is called as a dd transition. Okay, that's why it is called as a dd transition. Okay, similarly f transition. Okay, ff transition is also similar, but f, how many f orbitals are? So there are 7 f orbitals, 7 types of f orbitals are there. Okay, so similarly it will also, this d and f transitions are used to identify different type of metals. Okay, because in presence of ligand, their energy will be d orbital energy will be differentiate. Okay, and DD transition will be there, and it will give particular and intense color, which can be used to identify particular metal. Okay. So absorption peak will be depend position in the periodic table. Okay, so suppose you are taking iron, you are taking suppose other element like copper. Okay, so according to their position in the periodic table, means what we are going to say, that according to position of sample, suppose it is Fe3 and copper first. Okay, according to the position of sample, the d or d electron, number of d electron will be different. Okay, number of d electron will be different, and the dd transition also will be different. Okay, so due to difference dd transition, it will give different energy and different color. So it can be used to identify particular energy. Then it can also used for identify oxidation state. Okay, it will also affect dd transition. Okay, oxidation state, because if oxidation state is high, so electron will be less in dd orbital, and it will give different type of transition. Then nature of ligand, obviously nature of ligand also will affect the dd transition. Okay, why? Because ligand is responsible for splitting this d orbital in different energy. Okay, initially you can say all d orbitals has same energy. First, second, third, fourth, and fifth. So these are the d orbitals. Okay, initially it is look like that, but when ligand will be attack, okay, ligand will be attack on metal ion, this d orbital will be split in higher and lower energy. So there will be some energy gap, delta. Okay, and this energy gap is created by ligand. Okay, that's why ligand role is very important in dd transition also. Okay. So if your epsilon value is very high, okay, then you can measure very low concentration also. Okay, epsilon value should be very high, and it is epsilon value is generally higher for pi star transition. Okay, because it is symmetrically allowed transition, so the epsilon value is higher for pi star transition, and by measuring this transition, you can measure very low concentration of your analyte. Okay, so this should be kept in your mind. Okay, which absorption you will consider for your measure the concentration of analyte. So its epsilon value should be high for that. Then second question is why we are talking about this epsilon value is high. Okay, because to examine or to estimate accurate concentration of your analyte, the epsilon value will play a very important role. Because if epsilon value is very high, then it will give accurate result. Okay, and if epsilon value is low, then it is very hard to measure, and you will not get accurate result. Okay, so what we will do, suppose Fe plus 3 is there. Okay, so generally Fe plus 3, if it will precipitate as a hydroxide, it will also give reddish brown color, but it is not the epsilon value of this transition is not very good. Okay, so what we will do, we will add here thiocyanate SCN minus. Okay, so it will make so suppose it is like, so one side will be removed by thiocyanate ion, and it will give this type of complex. Why we are making this complex? Again, because its epsilon value is very high, and by making this complex you can identify. So now it will be overall complex, overall charge will be plus 2 only. Okay, so now because epsilon value is very high, so you can identify very less concentration of iron present in your analyte. Okay, and it is happening due to one more phenomena which is called as ligand metal charge transfer. Okay, what is meaning of that? Because it is iron Fe plus 3. Okay, iron in plus 3, so it is 3 times positive charged. Okay, so it is you can say electron deficient atom. Okay, in this complex iron Fe plus 3 is electron deficient center, where thiocyanate has negative charge, so it is electron rich center. Okay, so electron can jump from here to here. Okay, in molecular orbital theory you can understand better, but here for a outer idea or a basic idea you can understand that electron is going from thiocyanate to Fe. So thiocyanate is what? It is ligand and it is metal. So charge transfer from thiocyanate to metal is known as ligand metal charge transfer. Understood? It is a ligand to metal. Simple. Ligand to metal charge transfer. Okay, so ligand is thiocyanate and metal is Fe plus 3. Okay, similarly there is some cases where metal to ligand charge transfer. Okay, how it will be there, how it will be look like metal to ligand. So another it is iron complex, but now iron is in Fe plus 2 form. Okay, iron in Fe plus 2 form, and it is making complex with 110 phenethroline. Okay, when it is making complex with 110 phenethroline, then what will happen? It is look like, we can say only like that. Okay, I am not making full structure. Okay, so it will so what is happening here? It is iron plus 2. Okay, and iron has tendency to change Fe plus 2 to Fe plus 3. Okay, it will give electron. So this electron will move here to here. Okay, electron from iron, it will move from iron Fe plus 2 to 110 phenethroline. Okay, so it is metal and it is ligand. So this transition of electron will call as metal to ligand charge transfer. Okay, metal to ligand charge transfer. So I think it is clear how it is metal to ligand and ligand to metal. Okay, so ligand to metal we discussed first case, and here we discussed metal to ligand transfer. There is one more transfer, ligand to ligand charge transfer also is there. Okay, then we will discuss about applying Beer law to mixer. Okay, suppose your analyte has mixer of two compound like potassium chromate and potassium permanganate, then what will be the appearance of your spectrum? Okay. So it is also discussed by sir, but I will give you a basic idea. So suppose Cr2 is giving peak here. Okay, so suppose this is the peak of Cr2O7 minus 2 and another peak. Okay, so this is peak of MnO4. So MnO4. Okay, MnO4. So MnO4 minus, and it is a K2Cr2O7. So it is Cr2O7. Okay, so individually you will get peak like that. Okay, but if your analyte has this both ion, okay, then it will give a additional peak. Okay, so first of all it will give a peak, then it will give a CO2 sun. So this will be the final peak. Okay, this will be the final peak of your mixture of analyte. Okay, so like that you can for particular wavelength you can identify that this element is present, this compound is present, and this compound is also present. Okay, in my analyte. So similarly, if complex mixture is there, then you can identify according to peaks in your spectrograph. Okay, so it can be so spectrometer can use for quantitative analysis also. It has wide application, like we have discussed already, that organic, metal, drugs, okay, and biological system. It has high sensitivity. Okay, it can measure up to 10 power minus 4 to 10 power minus 5 concentration. Okay, it is very less. You can, if it is like, okay, and 0.000. Okay, so it is very less concentration. You can measure by spectrometer. Okay, high selectivity also. Okay, because particular metal will give particular wavelength, so it is very selective. Good accuracy. Okay, spectrometer has only 1 to 5% relative error, and it is very easy and convenience. Okay, because classical method of analyte, okay, in laboratory are taking very much time, but spectrometer is very convenient, and it is very useful for industrial application where we need result in short time. Okay, so for this purpose, and frequently, short time and frequently, so for this purpose spectrophotometer is very good technique and good thing to use. Okay, then similarly, in last lecture it is explained that aluminium Al+3 can be uh, identified by alizarin. Okay, so when it will make compound, it will also give colored compound. Okay, it will make ligand and it will colored compound, so you can identify this thing also. Similarly, iriochrome black, okay, which is also make compound, and will also give particular absorption at particular. Why we are using this type of organic compound? Because it has very high epsilon value. Okay, why it has a high epsilon value? Because this organic compound contain many chromophore. Okay, like that. So due to presence of this chromophore, it will give very intense color. Okay, so that's why we are discussing about this. So this thing that we just discussed a few minutes before, that to identify iron we used HCl. Okay, but if in your sample CO+2 cobalt and molybdenum, if this type of iron is present, then it will also give color. Okay, and it will then you will not get a correct reading. Okay, that's why these things should be kept in your mind. Okay, similarly, peroxide ion, suppose we are discussing about peroxide. What is peroxide? Peroxide, okay, you should know what is the peroxide. Okay, so what is different? This is the water. Okay, this is the structure of water. What is the peroxide? It will be like that. Okay, so one hydrogen will be removed from this side and one from this side. An electron will be given to oxygen because it is more electronegative. So minus and minus. So overall you can write like O2 minus 2. This is the peroxide. Okay, so this is also is good ligand, and it can be also used for analytical purpose, because it will also make complex which will give particular color to identify particular element. Okay, Then one more thing, that chromium, okay, it is Cr plus 3. If you see the structure of okay, Cr plus 3. So what is the electronic configuration? Why I am doing so? So you can understand better what is the actual concept behind that. 1s2, 2s2, 2p6, then 3s2, 3p6, okay, 4s2, then finally 3d. How much? 4 electron will be there. Okay, so Cr plus 3. So Cr plus 3 means 3 electrons are removed. So 2 electron will be removed from S and 1 electron from D. Okay, so don't worry about that. Why I am giving this idea is because when Cr plus 3 is oxidized, oxidizing means we are removing the electron. Okay, so when we are oxidizing it, it will convert in Cr4 minus 2. Okay, so how we will identify that it is oxidized? So whenever oxygen is added in anything, if oxygen is added, it is known as oxidation. Here also you can calculate its oxidation state. Okay, so what will be the oxidation state of chromium? So it will be you can say X. Oxygen is minus 2, so minus 2 into 4, and overall charge is minus 2. Okay, so X will be 8. It will be plus 6. Okay, if you will calculate, you will get X equal to 6. So here chromium has oxidation state 6. Okay. Now if it is in 6 plus 6 state, plus 6 oxidation state, then how much electron will you need to remove? You need to remove all d electron and 4s2 electron also. Okay. So finally your electronic configuration will be 4s0 and 4d0 also. Okay, so now it is clear that there is no d electron, so dd transition is not possible here. Okay, dd transition is not possible. So if dd transition is not possible, then what region is responsible for coloring of this compound? Okay, so what is the reason behind it? So just a minute. So here, although chromium color is not due to dd transition, but here is you can say oxygen. Okay, this is the Cr4 minus 2. Okay, it is Cr4. Okay, so oxygen has lone pair, and oxygen can give electron to chromium. Okay, so it will be again ligand to metal charge transfer. Okay, so this phenomena is responsible for the color. Okay, here it will be. Okay, so like that you get. Then organic molecule, we have already discussed why organic molecule give color, because they contain many type of chromatophore. Okay, one more thing, this is very important. Here we are discussing two things. First is identify of analyte, then separation also. How it will like that? Suppose you have nickel, Ni plus 2. Okay, and it is discussed many times that it will make complex with dimethyl glycol. Okay, but you need, okay, so after that suppose you have Ni DMG H2. Okay, suppose this is the complex, you need to separate it. Okay, so what you can do, suppose this nickel plus ion in your aqueous medium. Okay, suppose this nickel plus ion present in aqueous medium, then what you did, you dissolve this dimethyl glycol. This dimethyl glycol you dissolve in CHCl3, which is a nothing but a organic solvent. Okay, chloroform. So when you mix these two things, okay, chloroform will not dissolve in aqueous. Okay, so it will make separate layer. Suppose I am making a separating funnel, it will be look like that. It is not perfect, but yeah, you can understand. Okay, this is separating funnel. So what will happen? Because chloroform has higher density compared to water, it will be settled here, and water will be, because it is aqueous solution, so aqueous will be there. Initially, nickel was there, Na plus 2 was here, and here it was DMG, dimethyl glycol, in CHCl3. Okay, it will be in CHCl3. Okay, so what will happen now? Na plus 2 ion react with dimethyl glycol, and it come from aqueous to CHCl3. Okay, so all nickel ion which are present in aqueous solution come in CHCl3. Okay, in the organic solvent. Then you can separate it by opening this knob. You can separate your solution which contain only dimethyl glycol, no, not dimethyl, you can say Ni with dimethyl glycol complex. Okay, so this complex you can separate also, means identification and separation, both thing can be done by this method. Okay, so this is all about the concepts which are taught in this week 5. Okay, any doubt up to here you can ask, you can write me in chat box also. Okay, so we have discussed this thing, concepts of WEEK-5. Now we will discuss about the assignment of previous semester. Just wait for 5 minutes, okay, then we will start. Okay, student. Now we will discuss about the assignment number 5. Question number first. The incorrect statement for the Lambert-Beard law. Absorbance is directly proportional to the path length of the absorption medium. Okay, so this is the path length of absorbing medium is it is sample. Okay, so suppose here to here. Then absorbance is not affected by temperature. So first is this is correct. Then absorbance is not affected by temperature, pH and electrolyte concentration. Okay, so it is not correct. Then absorption spectra is plot of absorbance versus wavelength. Yeah, this is correct. And final, absorbance is directly proportional to concentration of absorbing species. This is also correct. Okay, so B will be the right answer of this question. Yeah. Okay, so the Beard-Lambert law states that there is a linear relationship between the concentration and absorbance of the solution. Okay, concentration and absorbance of the solution, which enable the concentration of solution to be calculated by me. Just a minute, somebody is getting up, I think. Okay, so the Beard-Lambert law states that there is a linear relationship between the concentration and absorption of solution, which enable the concentration of solution to be calculated by measuring its absorbance. Absorbance is directly proportional to the path length. Okay, so suppose this is the light and this sample, so it will be depend on the concentration of sample as well as the thickness of path length. Okay, so absorbance spectra, and then is absorption spectra is plot of absorbance versus wavelength. Okay, so we know that this type of curve is there. Okay, on x axis it is a lambda and in y axis it is absorbance. Absorbance is affected by temperature, pH, electrolyte concentration and influence of other elements also. Okay, so these things already discussed. Question number second is, what is the span of wavelength for UV visible spectroscopy? Okay, so we have already discussed. Okay, so 200 to 400, no, it is only for UV. Okay, so this is not correct. This wavelength is for only UV. Then 200 to 800, yeah, this is correct. Okay, because 200 to 400 UV wavelength. Then visible, we can say 400 to 800. Okay, so this is the, you can say this is the visible and this is not our case. Okay, so this is the right answer. B is the right answer of this question. Question number second. So the explanation of question number second is, ultraviolet visible area UV, it is known as UVVs, ultraviolet and visible spectrum. So this measurement span wavelength from 200 to 800 nanometer. Okay, please keep it in mind. The absorption by a molecule of ultraviolet or visible radiation result in transition between the molecules electron energy level. Okay, so what will the effect when this light will be fall on the molecule? It will be transition will be there. Okay, transition between the molecules electron energy. Okay, electrical energy level will be transition will be there. Okay, and the optical and electronic property of different materials such as film, powder, monolithic soil and liquid are suitable for characterization. UV visible spectroscopy is a cost-effective, simple, versatile, non-destructive. Non-destructive means your sample is not getting distracted here. Okay. Then analytical technique suitable for large spectrum of organic compound and some inorganic species also like metal and other compound. As a function of wavelength, UV visible spectrometer measure the absorption or transmutation of light passes through the medium. Okay, so transmutation and absorption both are contradictory. Okay, if absorption is high, then transmutation will be low and vice versa. Okay, then question number 3: which ion among the following, if present in color complex of metal, decrease the absorbance? Okay, so we have already discussed that phosphate and sulfate. Okay, phosphate and sulfate are right answer when it is there. Okay, the if present color complex metal ion decrease absorbance. Okay, so color complex due to presence of color complex. Okay, due to presence of color complex, the absorbance will be decreased if phosphate and sulfate is there. Okay, so what we will do? We need to carry out standard addition method here. Okay, to correct our result. So this is the explanation of question number 3. The absorbance of mainly colored complex of metal ion is decreased in presence of sulfate and phosphate because tendency of this ion to form colorless complex with metal ion. Okay, so when this okay, why we are worrying about that? Suppose you are metal and it is reacting with any ligand. Okay, plus, okay, and suppose it is making complex and it will give color. Okay, then what will happen if sulfate is present? Like sulfate is present. Okay, so if sulfate is present, then some amount of metal will be react with sulfate and it will give metal sulfate. Okay, MSO4. So it will be M2SO4. Okay, to satisfy that. Okay, so if this type of salt will be formed, then the means the quantity of this complex will be decreased. Okay, so the intensity of color will be decreased finally. Okay, so you will not get accurate reading of your metal ion present in your solution. Okay, that's why it will create problem. Then question number 4. Question number 4 is why acetone is not used as a solvent to measure any analyte absorbance in between the range 200 to 300 millimeter. Okay, why acetone is not used? Okay, so we will read this option one by one. Most of analyte are not suitable in acetone. Okay, then acetone has broad spectrum in range 210 to 300 nanometer, and acetone has no absorption spectra in 200 300 nanometer. Acetone has no relation with analyte absorbance. No, this is not correct, I think. Okay, so means acetone has absorption in this region. Okay, that's why if acetone will be absorb the radiation in this region, then how you will identify the analyte? Okay, so you will not get clear peak of analyte because acetone is interpreting your results. Okay, so suppose 200 to 320, you are going to suppose some analyte is present here which will give peak like that. Okay, but you are dissolving this compound in acetone, then acetone will give peak like that. Okay, then then the analyte peak will be you will not identify the analyte peak in the presence of acetone peak. Okay, So acetone peak will be dominant here. That's why you will get trouble, okay, to analyze your to identify your analyte here. Okay, that's why we are not used acetone. So I think this option is correct. It has 10 to 10 nanometer absorption spectrum. Okay. Okay, so this is the correct answer. So it has around 210 to 310 or something higher. Okay, so it will give peak in this area, a broad peak in this area, so that you cannot use here. Or if some analyte is giving peak at 270, which we discussed previously. Okay, so some organic compound which is giving peak here. Okay, but if acetone is there, then this peak will be merged. Okay, and you will not able to identify, you will get confused. Okay, so that is the reason why we are not using acetone in this reason. Okay. Then question number 5. Consider the following statement regarding the electronic spectra of metal complex. Okay. Consider the following statement regarding the electronic spectra, okay, of metal complex. Metals position in the periodic table, obviously. Okay, why it is so? Because as position of metal will be changed in periodic table, the number of d electron will also change. Sorry. So number of so d electron will be changed, and it will create different type of transition. Okay, and give different type of color. So this is correct. Then oxidation state of metal ion. Okay, then oxidation state of metal ion, obviously, if it is M+2 and M+3, then both will give different type of color. We have already explained iron, if it is Fe+2 and Fe+3. Okay, so what will happen in Fe+2 when it will make complex with ligand like 110 phenethroline? Then it will give metal to ligand charge transfer. But if it is Fe+3 and if it is making complex with thiocyanide, then it will give ligand to metal charge transfer. Okay, so these both cases are different here. Okay, both cases are different, and you will get different type of color, different type of intensity, or different type of wavelength. Okay, so these are the thing. So it is also depend on oxidation state of metal ion. Then third is nature of the ligand. Okay, obviously, if ligand is different, then different type of phenomena will be there. Okay, so it will depend on if it is a strong ligand, then it can give electron to metal. Otherwise, it will be not possible. Then it will not give color. So there are different type of things which can affect this transition. So this is correct. This is correct. And these three points are correct. Then fourth point is ligand do not affect electronic spectra. This is wrong. Okay, because we have already discussed that nature of ligand affect the spectra of metal ligand or any. Okay. So the right answer will be D. A, B. Okay, so this is the right answer. Okay, so D is right answer. Electronic spectra of metal complex depend on position of the metal ion in periodic table, their electronic configuration. Okay, electronic configuration means how many electron are d orbital, and if it is positive charge, then how it can accept electron from ligand and all these things. And distribution also of electronic orbital. It also depend upon their oxidation state. Okay. Then ligand bound with it. Okay. Which type of ligand is bound with it? It is also depend on that. Then whether the ligand is strong or weak. Okay. Electron donating capability NO. Okay, so so these all points are correct. Okay. Okay. Good question. Then question number 6. Identify the correct statement from the following for the two complexes Fe SCN plus 2 and here it is Fe plus 3. Okay, remember because SCN is minus, so overall charge is plus 2, but Fe is plus 3. And Fe phenolphthalein 3 plus 2 means here it is a Fe plus 2. Okay. Ligand LMCT we have already discussed, ligand to metal charge transfer, and MLCT means metal to ligand charge transfer. Okay. So what will be the correct answer? Both FeSCN and Fe phenolphthalein 3 plus 2, so LMCT no. FeSCN shows LMCT because it is Fe plus 3, so ligand to metal, yes, it is correct. Then Fe phenolphthalein 3 plus 2, so metal to ligand, yeah, because it is Fe plus 2. Okay, so electron will move from here to here, so metal to ligand. This is correct. No, this is also not correct. Then both metal, it's such a, okay, so B is our right answer. Okay, so this is the explanation. If the transfer occur from the molecular orbital with ligand like character to metal like one, the transition is called ligand to metal charge transfer. Okay, again I am reading. If the transfer occur from molecular orbital with ligand like character to the metal like one, okay, then it is called ligand to metal charge transfer. If the electron charge shift from molecular orbital with metal like character to the ligand like one, the band is called metal to ligand charge transfer. Means okay, so characteristic is what? Ligand like, means the electron is behaving like ligand like. Okay, so it is called as a metal ligand charge transfer. Here FeSCN electron transfer occur from ligand to metal molecular orbital, and Fe plus 3 electron transfer occur from metal to ligand molecular orbital. Okay, so we have explained about this. Okay. Then question number 7. Question number 7 is, in which case the organic molecule 1,2,4 tetrazool will show single smooth adsorption. Okay. So we have this topic, this question also we have discussed. Okay, gaseous mixture, Hexan mixture, aqueous solution. Okay, so gaseous mixture is what? It is only in vapor form. Okay, Hexan means it is polar, non-polar solvent, and aqueous is polar solvent. Okay, so we discussed in gases it will be all rotational vibrational peak. Okay, in Hexan solution it will give only electronic speed. Okay, but in polar it will give a broad peak light. Okay, so these are the different type of peaks. Okay, so in which case so single smooth edge. Okay, so we know that in aqueous solution it will give a single smooth. Okay, so I think C should be our answer. Yes. Okay, here you can see in vapor it is giving many peaks. Okay, why it is giving? Because due to rotational, vibrational, and electronic transition. Here only electronic transition is there, but here intermolecular interaction will be there, and due to that all electronic peaks will be merged, and it will give only one single peak light. Okay, so this is the case. Typically visible absorption spectra. The compound in 1, 2, 4, 5 tetragen in one. The spectrum is shown in the gas phase, where many lines due to electronic, vibrational and rotational spectra are seen. In non-polar solvent B, the electronic transition can be observed, but the vibrational and rotational structure has been lost here. Okay. In polar solvent C, the strong intermolecular force has caused the electronic peaks to blend together to give only a single smooth absorption peak, which can be seen here. Okay. Only single smooth peak. Okay. Okay, then question number 8. What will be the total absorbance for the mixture of KMnO4 and K2Cr27 at a single value? Okay, we have already discussed about that now. What will happen? Suppose Mn and chromium. So okay, suppose Mn is giving peak here and chromium is giving peak like that. Okay, so two peaks in opposite. Okay, so this peak is given by KMnO4 or MnO4 minus in the absence of K2Cr27. Okay, and this peak is given by K2Cr27 in absence of MnO4 minus. Okay, but if both are present, then addition will be there. Okay, so overall peak will be look like. Okay, overall peak will be look like. Okay, so like that you can find out that which compounds are present in your array. Okay, so addition will be there. Okay, or sum of their individual absorbers. Okay, so sum of their individual absorbers different of their so difference not correct. Sum of their is correct. Absorbance of KMnO4 because K2 has no absorbance. No, it is also not correct. And absorbance of K2Cr27 because KMnO4 has no. So this is also not correct. Okay. So A will be right answer. Okay. According to this graph, you can interpret which one is the right answer. Okay. This thing is already explained previously. Okay. And this is the explanation. According to the Lambert-Beer law, absorbance for a multi-component system at a single wavelength is the sum of individual absorbance. Both KMnO4 and K2Cr27 have absorbance. These are colored compound. The total absorbance of the solution at any given wavelength is equal to the sum of the absorbance of individual compound in the solution. This relationship makes it possible in principle to determine the concentration of individual component of mixture even their spectra overlap completely. Okay, so like that you can interpret. Okay, here it is given very nicely. Okay, so this is the M, this is the M curve. How it is giving peak here, whereas N curve is giving peak here. Okay, but separately. Okay, but both M and N are present, then it will give a summation peak line. Okay, right. So this is the resultant peak when M plus N both are present in your L. Okay, so next question: which chromophoric reagent is used for determination of unknown concentration of lead plus copper? Okay, so it is also discussed in a 5th lecture. Okay, the end of this one. Okay, so I think it is diphenyl dithiocarboxone. Okay, which can be used for lead. Okay, so this is the structure. Diphenyl means Okay, by name you can interpret the structure. Diphenyl means first phenyl, second phenyl. Then diphenyl, then diphenyl thio. Okay, so just a minute. Okay, so it will be diphenyl. Just a minute. Diphenyl dithiocarbonyl is used for determination of unknown concentration of lead plus 2 ion. This is a chromophoric reagent. Chromophoric means it has chromophores. Where is this one is chromophore? Okay, and this one is chromophore. So it is chromophoric reagent, and it has chelating group. Chelating means what? It can make bond with chelating means this name is come from crepe. How crepe can hold by its teeth. Okay, so it is like that. Okay, how we can handle. So suppose we discussed last class about we discussed EDTA na, in last class how EDTA can hold. Okay, so suppose this is the okay, so this is the structure of similarly. Okay, so it can make bond from here, two are here, and it can also make bond like that from here, because when hydrogen will be removed it will be O minus. Okay, so means how much? 1 2 3 4 5 6. Okay, so EDTA is hexadentate. Hexadentate means what? It can make bond by 6 dead. Okay, so that's why it will make a complex chelating. It is known as a chelating group. Okay, so this group is also has sorry, just a minute. Okay, similarly here this diphenyl dithiocarbonyl also has donor atom like nitrogen here. Okay, nitrogen sulfur is also here, so it can also make a chelating complex. Okay, so this is the chromophoric reagent, has a chelating group. It helps to detect unknown concentration of lead containing substance. Okay, contaminated water or any other food sample. Okay, so contamination of lead you can identify by this reagent. Okay, so this is the 9th question. And finally the last question is the carbonyl complex at which wavelength pi star transition takes place. Okay, so the carbonyl complex at which carbonyl complex is what? C double bond. Okay, it is known as a carbon. So here two type of transition is possible, and pi star and pi star. Okay, because oxygen has lone pair also, no? Two lone pair. So it can both type of transition is there, but pi transition is more important because it is symmetrical and epsilon value is very high. Okay, so we will select this type of transition, and where it will give, so it must give in it will be I think 190 to 200. Okay, somebody is getting on, let me check. Okay, so this is the last question. Okay, in case of unconjugated alkane, okay, unconjugated we have discussed because it is only CO. Okay, it is unconjugated. So pi pi takes place at 170 to 190. Okay, in carbonyl, pi pi star transition 190 nanometer. Epsilon value is 900. And other is n pi star transition 280 nanometer, but epsilon value is only 50. Okay, why we are focusing on pi pi star only? Because it has very high epsilon value. It will give very good result. Okay, that's why we are considering pi pi star transition. But in n pi star transition, epsilon value is only 50. Since n pi star transition is symmetrically forbidden. Okay, why it is symmetric forbidden? Because it is electrons are jumping from non-bonding, we can say non-bonding to pi star, anti-bonding, non-bonding to anti-bonding. Okay, so that's why it is not symmetric. It is symmetrical forbidden. But if it is pi pi star, okay, so bonding to anti-bonding and same type of orbital are there, so it is a symmetrical allowed. Okay, so these are the few reasons why we are selecting pi pi star. Okay, intensity of this transition is much lower than allowed transition. Okay, obviously we can see epsilon value is very low, 15 and 900, very huge difference. That's why this is the reason and why we are selecting this pi pi star transition. Okay, so this is all about this transition. Sorry, this question answer and assignment. Okay, assignment number 5. Now, if you have any doubt, any question, you can ask. Student, I think some students are there. Guna Sali and Karthik, you any doubt regarding this week? If you want to ask, then you can unmute, or you can write in chat box also if any doubt is there. I have already explained all the concept of week 5 as well as assignment of last semester. Okay. Okay. So I will upload this video because I think due to internet connection issue, you people not able to join me, but I will upload this video so you can go through it once again. Okay. Okay, then if you have no doubt, then you can leave. And I request all of you, please join interactive meeting. Okay, so if you will join live, then we can discuss some concept. Okay, and you can clear your doubts also. It will be more beneficial compared to see video after the class. Okay. Okay, so I am going to close the meeting. If you are in doubt, you can write. Okay, thank you very much. Okay, bye. gas.